from section 6.5 are on page 392, and one of them says, what if you have just a bunch of parallel lines? You don't know the spacing between them, you just know that the lines are parallel. So I'm going to put 3 lines up here, not equally spaced. They don't have to be. But I am going to say that the lines are parallel. So now we got all 3 lines parallel. I'm going to draw a couple of transversals, one here, and here's another one. 2 different transversals. The links that are cut off between these 2 transversals, because the lines are parallel, have to be in the same ratio on each segment. In other words, if I put A here and D down here, B on this one, and C over here. Well, what we're saying is the ratio of A to D is the same thing as B is to C. Now, when we were going over this section in class, we said, have you ever seen any parallel lines before? Well, yeah, you see some on music staffs, all right? So every time that you see a music staff, those little segments that are cut off on the bar lines, those are congruent segments. But if you had another one coming at an angle, it would also be cut off so that all the segments would be the same, because those parallel lines are equally spaced, right? And then the next theorem is theorem 6.7. I call this the splash theorem. You've got some triangle, all right? Let's just label this A, B, C, and you have an angle bisector. Well, I'm going to bisect this top angle here at A. There is the angle bisector. Now the 2 angles are the same, but the 2 segments, let's label this point where it hits as X. The segment on the right, CX, and the segment on the left are not the same length. The only time they're going to be the same length is if this triangle ABC is an isosceles triangle and A is the vertex angle, all right? So this is not isosceles, so these 2 segments are not congruent. However, look at the splash effect. If you come down from the angle that's been bisected and hit that side, BX, and then bounce back up to the original side of the triangle, that length, that ratio, is the same as this splash effect over here. In other words, the length of BX compared to the left side AB, that ratio is the same as CX over on the other side compared to its original side AC. That's another proportion that just happens to come about when you have an angle bisector. Only for an angle bisector. That's not a median or anything else. Okay? So that finishes section 5. Section 6 we skipped. And so section 7, the last one from this chapter, is on page 413. No. We skipped section 6, and that was the last one. All right, so that's the end of chapter 6. The big ideas are on page 413. You notice that the triangle similarity, angle-angle similarity, side-side-side similarity, side-angle-side similarity, those are the only 3 ways that we have of proving any 2 triangles similar to each other. And that's the end of chapter 6.